An oscilloscope is the most useful general purpose of all electrical measurement systems. Oscilloscopes display voltages as a function of time. This allows the user to interpret the data without making unwarranted assumptions. Oscilloscopes and voltmeters are both used to measure voltages. The difference is that voltmeters provide a single number which supposedly characterizes a signal. An oscilloscope, however, allows the user to view the time-varying function directly, so that no assumptions need to be made as to the actual signal shape. In fact, the voltmeter instrument and the scope instrument on the analog discovery share the same connectors, so only one of these instruments can access the connectors at any given time. Channel 1 of the oscilloscope uses the 1 plus and 1 minus terminals. As with the voltmeter, the 1 plus terminal is connected to an orange wire and the 1 minus terminal to an orange wire with a white stripe. Channel 2 uses the 2 plus and 2 minus terminals. The 2 plus terminal connects to a blue wire and the 2 minus terminal connects to a blue wire with a white stripe. The assumed polarities of the scope measurement are the same as the voltmeter. The positive terminals are connected to the assumed positive voltage, and the negative terminals are connected to the assumed negative voltages. To demonstrate use of the oscilloscope, I'll measure voltages in this circuit. The power supply will apply a time-varying voltage to the circuit, and we'll use channel 2 of the oscilloscope to measure the resistor's voltage, and channel 1 will measure the voltage across the diode. This is our circuit. We'll apply a time-varying voltage with channel 1 of the waveform generator, the yellow wire. Ground is here, and we can use any black wire to make that connection. We'll use channel 1 of the oscilloscope, the 2 orange wires, to measure the voltage across the diode. And we'll use the 2 blue wires to measure the voltage across the resistor. Now we're ready to test our circuit. We'll use the WaveGen instrument to apply a low frequency triangular wave, the frequency of 13 Hertz, and an amplitude of 5 volts. Click on Run to apply power to the circuit. The diode lights up when the voltage across the diode exceeds about 2 volts, so the diode blinks 13 times per second. Now let's use our oscilloscope to display the resistor and diode voltages. To open the oscilloscope, click on the scope icon on the welcome window. The Analog Discovery Oscilloscope has a lot of features, but in this tutorial I'll only present the basic use of the oscilloscope. In order to start acquiring and displaying data, click on the Run button on the oscilloscope window. To stop acquiring data, click on the Stop. The data as a function of time is displayed in the main window. The horizontal axis of the main window is time, and the vertical axis is voltage. At the moment, the data is badly scaled, so we need to adjust the waveform window properties. These parameters are controlled with these panels on the right-hand side of the oscilloscope window. The horizontal axis properties are set with the time controls here at the top. The base option sets what's called the time base. That's just the scale on the horizontal axis. Its units are seconds per division. The number you select here sets the amount of time between horizontal divisions on the window. For example, if I change this to 100 milliseconds per division, the time between these vertical lines is 0.1 seconds. The position option adjusts where 0 time shows up on the window. If I change to 200 milliseconds, the 0 time shifts left on the main axis by 0.2 seconds. 0 time is also indicated by this black triangle at the top of the window. You can shift 0 time by clicking and dragging on this triangle. The vertical axis properties are set by the channel 1 and channel 2 controls. The vertical axes for each channel are set separately, so they may not share the same vertical scale. The vertical scale for the window over here on the left is indicated in a color that's appropriate for the channel scale that's being displayed. I can click on the little tabs here to change the channel that sets the vertical axis display. The scale on each vertical axis is set with the range option. For example, let's set the range on channel 2 to 2 volts per division. Notice that the vertical scale on the waveform window over on the left changes accordingly. The offset option sets where on the waveform the 0 volt display appears. For example, the channel 1 offset is initially 0 volts, so 0 volts shows up in the center of the screen. I'll change the offset of channel 2 to -1 volt. This shifts the entire scale on the left side of the screen down by 1 volt. 0 volts is also indicated on each channel by the rightward pointing triangles at the left edge of the screen. You can change the offset by clicking and dragging on these triangles. Next, let's look at the modes we can use to display the data. I'll talk about triggering later, but for now, let's switch that to none. By default, for higher time bases, 100 milliseconds or larger, screen is displayed. In this mode, the data scrolls past the window as shown here. Once it gets to the right edge of the window, it starts over again at the left side of the window, erasing the previous frame of data as it goes. Let's change this to shift. The main window will now shift to follow the waveform. Once the waveform reaches the right side of the window, the waveform will slide to the left so that the new data points always appear at the right-hand side of the screen. If we select repeated in the run options, the oscilloscope displays one window's worth of data at a time. The window of data is refreshed all at once when the entire data set is acquired. We're seeing snapshots of the data in the main window. If the time base is low, less than 100 milliseconds per division, the oscilloscope always displays the data in repeat mode. Let's change our time base to 20 milliseconds per division. Now we can see a lot of detail in our signal, but it keeps jumping around. In repeated mode, the oscilloscope displays frames of data, much in the way a movie is composed of static picture frames which are successively displayed to give the impression of movement. What we need to do is make the successive pictures coalesce to create a coherent display. On an oscilloscope, this is usually done by setting what is called a trigger. Usually, oscilloscopes show one window's worth of data at a time. An oscilloscope will display these short chunks of data as a set of successive snapshots, like the frames of a movie. Suppose these snapshots of data are chosen at some arbitrary interval, as shown here. These successive frames are not consistent, and they probably end up looking like a flickering jumble of lines. We want to be able to choose our frames of data so that some feature on the data lines up at the same time in all of the snapshots. This feature is called a trigger point. So now let's take a look at what happens if we acquire our data based on a trigger point. In the example shown here, we are triggering, that is, acquiring our frames of data based on the value of the signal being here and the slope of the signal being positive. Now the frames of our movie all look the same. The waveform will appear to be frozen and we can read the data we need at our leisure. To trigger the data, let's set the trigger mode to normal. Notice that the signal seems to freeze now, creating a very easy to read display. What's happening is that the trigger is now forcing all of our frames of data to line up so that it appears that the data isn't changing. The trigger point corresponds to a set of conditions which the scope will look for in your signal. A typical trigger point is defined by a voltage level and a slope condition. The voltage level is fairly self-explanatory. It's simply the value of voltage at which the trigger condition occurs. The slope condition defines whether the trigger point is set based on the signal increasing, called a rising edge trigger, or decreasing, called a falling edge trigger. The trigger source also needs to be defined. This menu allows you to choose from a variety of sources. Currently, we're triggering off of channel 1 on a rising edge with a 0 volt level. The defined feature, a 0 volt level, while the voltage is increasing, now lines up with 0 time in the main window. The 0 time is indicated by this black triangle at the top of the main window. Every frame of data lines these points up at 0, so the point where the orange line goes through 0 volts and is increasing gets placed at the center of the screen. Since the signal repeats itself at regular intervals, the successive frames give the impression that the waveform isn't changing at all, and it makes it easy to make our measurements. Changing the trigger level just changes the voltage that corresponds to 0 time. If I change the trigger level to 1 volt, the wave shifts so that the waveform crosses 1 volt at time t equal to 0. We can also change our trigger level by clicking and dragging the triangle at the right of the screen. We can change the location of 0 time by clicking and dragging the black triangle at the top of the screen.